Hello all, welcome back to my YouTube channel all about VLSI. In this particular video, we are going to discuss about RISC-V processor design, and this is a series of RISC-V processor design where previously we have discussed about register file unit and how actually you're going to fetch the data and how actually you're going to fetch the data and instructions, right? And generally we know that we are going to store the instructions in instruction memory, and we are going to use instruction fetch unit for fetching my instructions, and we are going to store the data in data memory, and we are going to fetch the data using data fetch unit, and we are going to store it in our instruction cache instructions, and data will be stored in data cache. That is what we know. And basically we many people have this two kind of doubts, that how instructions are converted into memory. How instructions are converted into binary and it is stored in memory, and how data is being converted into a binary and it is stored, and how actually the process is going to happen. And the second question is, do really the instructions and data have separate dedicated memories? So memory is not that much cheap nowadays, right? So you cannot have dedicated separate memory chips for your instruction and memory. Uh, instruction and data. No, that is not going to happen in our practical things. So how then the instructions and data are being stored? That is what we are going to discuss. That is nothing but my modified hardware architecture. So that is what we are going to learn in this particular session, so that we will have an idea, if we are working with RISC-V, how actually instructions are being fetched and how actually the data is being fetched. That is what we are going to know, right? Now, so we are going to have something known as RISC-V toolchain, and we are going to learn about something known as linker, and we are going to discuss about actual memory layout which we are going to have. So that is today's session agenda, where we are going to discuss about what do you mean by tool chain, how exactly the compilation pipeline is going to happen, what do you mean by preprocessor, compiler, and assembler, and what do you mean by ELF object file format, and what exactly an ELF file is going to have, and what do you mean by linking, and what do you mean by linker script, and what is a memory mapping, and what is exactly how exactly your instructions and data are being stored inside a single memory. Okay, so we are not going to have a separate dedicated memories. Yes, in theory, when we are learning about computer organization, we have seen that we will have separate dedicated memories for our instructions and data, but in practical, when we are working, we are not going to have separate chips. We are going to have a same memory where everything is being organized. Okay, that is what we are going to discuss it now. First of all, let us see what do you mean by tool chain. So basically, a tool chain is a complete set of programs that basically turns human written source code into a binary CPU that will be executing. Okay, so that is nothing but my tool chain. So whatever the .c file in the C language we are going to write down, right, that will be converted into executable memory image that will be executed on your hardware. And this particular process of conversion is done by our tool chain. And for RISC-V, we are going to have a separate toolchain which is known as RISC-V GNU toolchain, and which is a compiler, assembler, linker, and supporting utilities. It is going to have all this. It is going to have all these particular utilities which are present inside this particular toolchain, and it is going to target for RV32 or RV64 instruction set architecture. Okay, and we haven't started yet discussing about RV32 instruction set architecture or RV64 instruction set architecture, that we are going to discuss in our next sessions. But in this session, we need to understand how this particular instructions and data are being stored inside memory, and what is the process, like if a user is writing down a .c file, how that particular .c file is being converted into actual executable file, and what is the process which is happening. We are not going to discuss in great detail, but we are going to discuss an overview of this particular thing. And the tool is going to do one particular job, and it is going to pass this particular outputs to the next. So it's not a monolithic program. We are going to have a kind of immediate intermediate files we are going to have, right? Now, so this is what I was talking about. So whatever the .c file or the c coding we are going to write, that is our .c file. And we are going to have a pre-processor stage which is going to expand this particular .c file, and the compiler is going to basically compile whatever the .c file we are going to write down, and it is going to convert it into an assembly file which is known as .s file. And this particular .s file will be used by the assembler, and it is going to generate something known as .o file, which is not nothing but an object file. And linker is going to merge all this particular object files into a single file, and it is going to convert, or it is going to produce it an .elf file which is being loaded into our hardware. This is what the overall process is going to look like. Now, first of all, let us try to understand what is a preprocessor. So preprocessor is basically having a .c file with it. That means whatever the C code we are going to write down, right, that my preprocessor is going to use. So this particular preprocessor is the stage one where it is going to handle everything, which is going to start with hash include, like hash define or hash if def. So these are all my macros, right? So these are going to be expanded, and it is going to basically expand it everything, and whatever the definitions, whatever the libraries which are going to have, it is going to expand. And the output of this particular preprocessor is a plain C with no preprocessor directives left out, and it's a single expanded translation unit. That is what it is going to do. That is what expansion is. So whatever the hash include or hash define or whatever the macros which are there, which were those will be expanded by this preprocessor, and it is going to give me expanded file which is known as .i file, which is not going to have any macros or any particular uh, preprocessor defined things, right? Now, next is compiler. So after preprocessor done its job, that will be this particular file will be generated, which is known as .i file. And using this .i file, compiler is going to compile it, and it is going to generate the assembly file. So the compiler is going to basically translates the expanded C source into RISC-V assembly, which is nothing but my human readable form of instructions from ISA doc. This is what we are going to learn in our future sessions. We are going to learn about the instruction set architecture, and we are going to see what are the different kind of instructions which we have and which are human understandable, because those are nothing but my instruction set architecture, right? And that is what my compiler is going to do. Basically, it is going to compile my .c file into this particular human understandable instruction set code, and it is also going to perform optimization, register allocation, and type checking along the way. And the output of this particular compiler, as I've said you previously, it is nothing but my .s file, which is only containing mnemonics of my assembly, and it is not a machine code yet. It's just converted into an assembly file. That's it. Now, after compiler has converted this particular expanded C file into a particular assembly file, that particular file is going to have a format of .s, and this particular .s is given to a assembler. Now, what assembler is going to do? This assembler is going to basically translate human readable assembly mnemonics into actual machine code. So I will show you in the next sessions where we are going to have an instruction like, let's say suppose add I r1 comma r2 something, some random assembly code which we are going to have, and this particular assembly code will be converted into your 32-bit binary format, and this will be done using this assembler. So assembler is going to basically convert this particular whatever the instructions which my compiler has converted, or the human understandable instructions, into a binary, actual binary format by this assembler. And it is going to generate one particular file which is known as .o file, and it is known as relocatable object file, and it is not yet programmable. And here, see, whatever the binary file, whatever the binary instructions my assembler is going to generate, whatever the instructions we have, right, human understandable instructions, that will be converted into binary format by the assembler. And whatever the binary format instructions which are there, right, so this should be given some kind of addresses. Okay, so these addresses are not given by the assembler yet, and it has just given me a particular .o file which is in binary format, and it is relocatable in the sense no final addresses are being given. Those particular final addresses will be given by the linker. So that is what it is written. So a .o file is when you write an assembly program, and it cannot directly become an executable because many details like final memory addresses are still unknown, and assembler is only going to convert the assembly code into an .o file. That's it. And this particular .o file which was generated by the assembler is not yet executable, and it's an intermediate file itself. And why the assembler is not generating an executable file? Because we might have many different files like main.s or math.s or uad.s. So we can have multiple files, and for multiple files we will be having multiple object files. So for this multiple object files, at this particular stage, assembler is not going to know where these files will be placed in the memory. Okay, so that is the reason we are this assembler duty is to convert this assembly code into binary code, that is nothing but my .o file, and this can be relocatable. That like where exactly this piece of binary information should be placed into the memory, it's not the duty of my assembler, it's the duty of my linker. Okay, now this .o file is going to have some kind of syntax kind of thing, which is nothing but my elf object file format. So if an object file has been generated by the assembler, it is going to have some kind of file format, which is nothing but my elf file format. And this particular elf, which is nothing but executable and linkable format, is the container format for both .o files and final executable use. And it's not just a raw machine code which assembler is going to generate. So it's not like binary ones and zeros, it is not, it is going to generate. No, it's kind of organized into named sections, and it is going to have some kind of metadata describing them. So every .o file and final linkable binary are both elf files. It is going to have some kind of format. We think it's just simply zeros and ones, which is assembler is going to generate, but no, it is going to have some kind of format. Okay, and a relocatable object file is an intermediate binary file generated by the assembler or the compiler that contains machine code, but its final memory addresses are not yet decided. This is what I've told you in the previous slides, and this is why a relocatable it is known as relocatable, because it can be placed or relocated anywhere in the memory by the linker. Now let us see the format of this particular .o file which my assembler has generated. So this is what the format of .o file which my assembler has generated, where the first section is nothing but my elf header. This particular section describes me the object file, like what kind of file type or what kind of architecture it is going to use, and what entry information and section locations and all. And this particular section is used by the linker or the loader or the debugger. And next section is dot text. So this basically stores the executable code. That means whatever the machine instructions or the 32-bit RISC-V instruction encodings, and CPU is going to execute this instructions. So this particular section is going to have the dot text. And next section is dot data. So it is going to store all the initialized global or the static variables, and it basically going to contain the variables with all the initial values declared, and it is going to use by the program at the runtime. And next is .bss file, where it is going to reserve space for uninitialized global or static data. And next is .ro data, where it is going to store all the store it is going to basically store all the read only data. And next is symbol table, where it is going to map names to the locations. And next is basically this symbol table is going to have all the function names, global variables, offset, and symbol types. Next is relocatable table, where it is going to records the place needing address updates, where it is going to have all the offsets and referencer symbols. Like this, it have many particular sections we are not going to detail in discuss. Like you need to know that assembler is not only going to generate some kind of binary information, but it is going to generate a .o file, where that particular file is going to have different kind of sections, where each section have its own meaning. And whatever the sections it has generated, it has not got any particular address, right? So this is nothing but my .o file, which is basically following the format of elf object file format. Next, so that is what I've told you. It is going to have different kind of sections. And next we are going to have something known as linker. So linker is going to basically combine multiple separated compiled .o files into a single executable file, and it is going to resolve symbol references. For example, if file A calls a function defined in file B, the linker is going to connect the call to the real addresses, and it is also going to assign the final concrete addresses to every section and symbol, something the compiler or assembler couldn't do alone. That is what I was saying in the previous slide. So assembler is going to basically provide the address to each and every section, right? And next, symbol resolution and relocation. So each .o file has undefined symbols. For example, a call to a function that lives in a different file. So linker is going to scan every particular symbol table, matches each undefined reference to its actual definition elsewhere, and it is going to basically relocation entries mark exactly which particular byte in the code need to be patched once the real address is known. So this is what my linker is going to do. And we are going to have something known as a linker script. Basically it's a kind of dot text file. It's kind of a dot ld file. The extension of this particular linker script is dot ld file, which is going to tell me, which is going to tell the linker exactly where in memory each particular section should be placed. We have seen the .o file format, we had different sections, right? So linker script will be generated, and it is going to tell the linker that where exactly in the memory each particular section should be placed. And without a linker, it is fine for a PC. It is going to use a generic default layout for a PC, and it is meaningless for a specific embedded memory mapping. If you are having a bare metal, then the linker script is very much necessary. And using this linker script only, we are going to basically store each particular section of data in a memory. And let me show you how it is going to look like. Yeah, so this is how the memory layout is going to look like. We are going to have a stack, and we are going to have a heap, and in between we are going to have a memory space. And we have seen, right, we have different sections of our elf file, like .bss, .data, ram base, or .ro data, and .text. So see, so .text is the section which have got the offset addresses this, and .ro data got the starting address as this, and ram base got the starting address as this, and .data have got the starting offset address as this. So you can see initialized global variables are present in this particular section, and it got the address as this. So like this, linker is going to basically provide, for each section it is going to provide a specific set of offset addresses. Now, after this, what is going to happen? So it is going to generate, linker is going to generate a file which is known as .elf. So this .elf is not yet the final file that will be executed. So program.elf, still it is going to carry some kind of headers and metadata, and which cannot be loaded into directly into the memory. So we are going to have something known as object copy. So which is going to strip away all the particular metadata and headers, and it is going to convert it into the final raw binary or the hex data, where from Verilog we are going to actually fetch it using the instruction fetch unit or the data fetch unit. We are going to fetch this particular binary data. Now, how instructions and data land in iCache and dcache. So basically, here, whatever the data which we are going to store it into my memory, that will be fetched. So instruction fetch unit is going to fetch the instructions from the dot text unit. We have seen, right? So dot text unit is a section where we are going to store instructions, entry point, and everything, and it is having the starting address as 0. So instruction fetch unit knows this particular address, and this is going to fetch the instructions from this particular unit. And dcache is, it is going to fetch the data from data bss. So basically we have seen, right, so here the dot data is having the addresses, this particular address, and my data fetch unit is, it is going to, or the dcache unit, it is going to fetch this particular instructions from this particular locations. This is how, using a single memory, we are trying to store the data and instructions in separate kind of sections, and the duty of the linker is basically going to allocate different kind of addresses for the data and instructions separately, and it's kind of very organized memory where we are going to use. And basically this instruction memory and data memory, what we have learned is it will be separate. That is what we have learned, but practically when we are going to work, it is a single memory we are going to have, but all the sections will be neatly organized, and the linker's duty is to organize and provide addresses for each and every particular section. And according to the linker information, the address information which we have got, my instruction fetch unit and data fetch unit is going to fetch that. Okay, so that is what I was saying about. So this is what we are going to build, right? So instruction fetch unit is going to fetch the data, and that will be stored in your iCache, and memory fetch unit, it is going to fetch the data and it is going to store it in dcache, and using the AXA interconnect we are going to get the instructions and data, and we are going to basically work with them. That is what we are going to learn. And so .c file will be basically preprocessed, and compiler is going to compile it, and assembler is going to convert it. .o file and linker is going to group them all, and it is going to basically provide the addresses for each and every particular section, and we are going to get an ELF file, and from the ELF file we are going to give it to object copy, and from that actual memory image will be generated, that will be given, that will be fetched by our iCache or dcache. So that is what we are going to have, and the key takeaways of this particular section is, so we have learned about what do you mean by tool chain, what do you mean by linker script, what do you mean by linker, and how exactly the instructions and data are being stored inside a single. So that's about this particular video. If you like this video, please like, share, and subscribe to my YouTube channel all about VLSI. Thank you for watching this video.